Stanford University.
All right, good afternoon, guys. Welcome back. We're already on Lecture 5, CS193P, and it's actually pretty exciting because today we're really going to get into some of the really exciting meat of the foundations of what we're going to be working with for the rest of the semester. We've been talking about some of the building blocks. We talked about the language, memory management, that kind of stuff. But today we're going to be talking about views and animations and drawing things to the screen. And this is where the iPhone really starts to stand out from all the other platforms that you've probably worked on in the past. The views that we'll be talking about today and some of the core animation framework that underlies the views are incredibly powerful. And they're pretty different from some of the view implementations on other platforms. We'll talk about why, but they really enable you to do some of these incredible fluid interfaces with animation and all these fancy things. And it makes it really easy to do it. So it's actually, I'm pretty excited. I was putting together a demo for afterwards and getting excited about just how cool some of this stuff is. So I hope you guys get pretty excited about it too. So before we get into that, we got some announcements. Assignment 1 grades were sent out. If you didn't get yours, contact Paul or Dave. They can get you some information on what happened there. Also, contact them if you need a loaner iPod Touch. We have a few now. They're available. So if you don't have your own device and you want to do on-device development, get a hold of those guys, and they'll hook you up with loaner iPod Touch. And finally, tomorrow, 120, assignment 2A and 2B are due. So hopefully you've all gotten a good start on that. Good to go. Before we get into all this stuff today, any questions from Monday, from Tuesday, Thursday, last week, that one. The stuff that Al talked about with model view controller, interface builder, nibs, the assignment, anything? All right. So today, as I said, we're going to talk about views. We'll talk about drawing. We'll talk about text and images. And we'll talk about animation. And so let's get into it. First thing, views. So views are going to be the foundation of all of the rest of this stuff. So first off, we probably want to figure out what a view is. So a view is a rectangular area of the screen. It's got a rectangle, and it occupies some space on screen. It has two main purposes. The first purpose is to draw content. All of the content that you're going to see on screen and do any drawing in, all of that is going to be appearing in a view. And its second main purpose is to do event handling. So when the fingers come down on the screen on the iPod or on the iPhone, the system figures out what view needs to handle those events. So all of the event routing is done based on views. So those are its main two purposes. UI view is actually a subclass of a class called UI responder. We're not going to talk about that a lot today. We'll get into it more when we talk about the specifics of event handling with touch processing. But it's a subclass of NSObject that knows how to implement some basic behaviors for touch handling. For the most part, actually, it just defines a protocol. There's actually not a whole lot of implementation to it. But it does some of the basic things for you. And UI view is a subclass of that. So it inherits the event handling behaviors from UI responder. Views are actually arranged hierarchically on the iPhone. And this is pretty similar to other platforms as well. You'll have some root view. And views are then subviews of their superview. Every view has a single superview. It can only be parented in one thing. But it may have multiple subviews. It has a whole array of subviews. And that array is ordered, and the order dictates what order they appear in on screen. So if you have one view and it overlays, or it comes after another view in its superviews subview list, sorry, kind of throwing a lot around there, then the second one is going to appear on top of the first one and will actually obscure it. So as I mentioned, every view, since it's a hierarchy, has to have some root. There has to be some view at some point that doesn't actually have a superview. And we actually have a separate class that represents that particular special kind of root view, and that's UI window. UI window, unlike on other platforms where a window is some sort of special top-level object, it's a whole separate thing, separate from a view. UI window on iPhone is actually just a subclass of UI view that has a few extra added behaviors to make it know how to be one of these root views to not have a superview. So the only view that you can have that displays on screen without having a superview on the iPhone has to be a UI window. And actually, an iPhone application generally only has one UI window. This is kind of different from what you might expect on other platforms. On Mac OS X and on Windows, individual applications might actually have multiple windows. You might have a window for a dialog box and other things popping up. On the iPhone, you really just have one UI window. And all of your views that go in there are what you build your application out of. This may sound a little bit strange at first and might seem a little bit limiting, but when we get into a little bit more of the core animation framework later, and talk about how that stuff works, it's pretty powerful. And you'll really find that you actually don't need multiple windows. You can just add extra subviews to the one that you've got and do everything that you could and everything that you'd want to do on other platforms just within your single UI window using UI views. So now you've got some idea of what the view hierarchy is going to look like. How are we going to create this? How do you get things into the view hierarchy? How do you shift them around? You've already seen a bit of that, and you can actually do a lot of it in Interface Builder visually. You create a new nib, and you can drag different pieces out of the inspector palette on the right-hand side, and you can build your user interface visually right in Interface Builder. You can define the subview relationships by dragging one view into another. Interface Builder kind of highlights which piece of the interface is being which view you're using as your super view. As you drag a view around in Interface Builder, it'll highlight whatever view is going to become that view's super view when you drop. But there are times where you might want to actually do this in code. And one of the most common cases of that kind of thing will be something like UI table view, which we'll talk about in some later lectures. It's basically where you're creating some sort of view hierarchy where the number of views that you're going to need isn't predefined. So if you have a list of things and the number of items in that list is determined at runtime, so you may have n items, you're going to have to create those views programmatically because you can't create them in the nib. You don't know at build time when you're creating the nib how many you're going to need. And the way that you'll get those into your view hierarchy is using UI views methods add subview and remove from superview. So if you want to add a subview to another view, you tell the superview to add some subview to it. If you want to take a view out of your view hierarchy, you don't tell its superview to remove the subview. You actually tell the view itself to remove itself from the view hierarchy. So you say view remove from superview, and that takes it out of the view hierarchy. If you want to shuffle things around within the view hierarchy, we said we have this array of subviews on every view. You might need to insert things at different points or move one view on top of another to determine the layout and the ordering. You can use the insert subview, insert subviews, insert subview at index or below and above another subview. And you can also exchange a subview at one index with a subview at another to just swap their position in that array. So the other thing to know about view hierarchies here is that the superview actually takes ownership of its subviews when you add a subview to a superview. It takes a retain on that object. So when you call view add subview my other view's retain count gets incremented by the superview. So the superview now has an owned retain on that. So if you don't actually need to keep a pointer to your subview around, like if it's a label or something that you're going to set and create once but never change any properties on, you don't have to keep a pointer to it. You can immediately release it because the superview is now holding a retain count. You're releasing it will release your retain on it, and the superview will just release it whenever the superview goes away. The memory management is managed by the superview in that case. It's actually not uncommon for views to only be retained by their superview. And in fact, if you create just a bunch of views in Interface Builder and drag them out into your window and start adding more in there, you're not actually holding any references to most of those views. Their only retain count is actually held by their superview. Another thing to keep in mind here, if you want something to not be drawn on screen, you don't necessarily have to remove it from the view hierarchy. There's a property on UI view called hidden, and if you set that to yes, it just tells the rendering pass to not draw it. Nothing that's in that view will show up on screen. So you can leave it in the view hierarchy. It can still be retained by its superview. It just won't draw and won't participate in event handling. So there's a few other structures that we're going to be talking about. Oh yeah, what's up?
So you mentioned that each of the views is only retained by the superview. So why do we need to release it in the objects that we create? We normally have to release them, right?
So the question is, if you have a view and I said it's retained by its superview, why do we have to release it when we're creating it? Probably it would have been a little easier to see with an example. But so when you're creating a new view programmatically, the way that you'll do that, let's assume we want to create a new UI button. You'll do UI button alloc init with frame, and then the frame that you want to, we'll talk about frame in a bit. It's a rectangle, the area on screen where it's going to show up. And then you'll call superview add subview that view. So now you will have one retain count because you called alloc on UI button. So you have a retain on that. The add subview, the superview just took another retain. So now the retain count of this UI view is now at 2. If you're not going to keep the pointer to that, you need to release your retain count, or else you're going to leak that view later. So you release after you've called add subview, the retain count goes back down to 1, and now the only person holding that retain count is the superview. So when the superview goes away, then it's going to call release on the subview, and that will actually deallocate it.
I actually meant the labels that you drag to the interface builder iPhone simulator thing. You actually drag labels and stuff, and then you have to release them back in the code, in the object that you, I mean, you have a pointer from the object to that particular label, and so you have to release it, right? In the deallocate function for.
Yeah, so question is, why do you have to deallocate something in Interface Builder? When you can set up a connection in Interface Builder, that actually, when that nib gets loaded, it calls retain on each of the objects that it brings in, because it's frozen these objects and then it retains them, so there's a retain count of 1. So when your view controller or whatever's holding on to that nib goes away, that's when you want to release each of the items that you have reference to, that you have connections to. Does that make sense? Yeah.
Sorry, I misunderstood the question there. Okay, so there's a few structures. These are actually struct types that we're going to be using for the rest of the day, and you'll see a lot later. So we should just quickly go over them. The first is a CG point. CG stands for Core Graphics. It's one of our graphics libraries on the iPhone. We use it for drawing, and we use its structures to define rectangles, points, and sizes. So CG point defines a point, an x and a y, and now all of these values are actually floating point values. So they're not necessarily whole numbers, they're any floating point value. CG size defines a size, a width, and a height. And CG rect combines actually a point and a size together. So a CG rect is a struct that contains both a CG point and a CG size. So it actually has 4 float values, an x, a y, a width, and a height. And we'll see what we're going to use those for in a second. But sort of visually what that looks like is this. We've got a CG rect, which is composed of that, as we just said, an origin and a size. The origin is a CG point, and the size is a CG size. So in this case, we have a rect that has, it's positioned at 8054, and its size is 144 by 72. So those are the three structs that we'll be seeing a lot. That's what they look like. We actually have some convenience macros to construct these things. As I said, they're just structs, so you actually could define them just as structs and access their individual elements directly. But there's these convenience functions, so if you need to create one inside of a line of code, you can just call one of these to create it. There's CG point make, which makes a CG point out of an x and a y. CG size make, to make one out of a size out of a width and a height. And CG rect make, to make a rectangle out of an x, y, width, and height. And you can see a couple examples here of how that's used. For example, in the CG point make, we're calling it with a x of 100 and a y of 200, which is equivalent to having allocated a CG, or created a CG point on the stack, and then just assigning point.x and point.y to 330. They're the same thing. Yes?
Is the xy coordinate in CG rect the top left arm?
So the question is the xy of CG point in the top left? And for all the cases on the iPhone where you're going to be interacting with views, that's absolutely the case. CG point could be used for anything. So, I mean, if you were using it in your own other situation, it could be whatever you want. Yeah, so if you're using it on the iPhone in views, if you're using it on the Mac, then it's actually bottom left. But we'll talk about that in a minute too. But yeah, the origin is always top left on the iPhone. The origin is in the top left. So y-axis goes downwards. This is the opposite of what you might be used to if you've done any programming on the Mac. So yeah, your UI view, origin's top left, X goes across, that's pretty standard, Y goes down. A view's location and size is expressed in 2 ways, and there's actually a little bit more to this. We're going to spend a little bit of time talking about it, but this is kind of the broad overview. The first way that you express the position of a view in its superview is using the frame. So the frame is the superview's size and location, the view's size and location in its superview's coordinate system. Then the second rect that we're interested in is the bounds. The bounds is the size of the view in its own coordinate system. So let's take a quick look at that. We've got a view A. Let's assume that its superview is the exact same size of it. It's positioned directly on top. So in that case, its frame is going to be 0, 0, because its origin is at 0, 0 in its superview's coordinate system. And its width and height will be 550 and 400 in this case. We're just picking some arbitrary sizes. So that's the frame. It's It's the rectangle that defines the size and location of the view in its Superviews coordinate system. Yeah, as we said, frame origin is 0, 0, size 550 by 400. In this case, the bounds is actually the same thing because the bounds defines the size of the view in its own coordinate system. There are cases that the bounds origin won't be 0, 0. We're not going to see any of those today, and we won't talk about that much. If you look into it a little bit more in more depth, you'll end up seeing that that's useful in cases where we start talking about UI table view and UI scroll view. Scrolling on iPhone is actually implemented by manipulating the view's bounds origin. But for most cases, you're not going to deal with that. You probably won't see it very much. Most of the times where you're looking at it, bounds origin will always be 0, 0. And then the size determines the size in the view's coordinate system, in its own coordinate system. So now if we create a new view in here, view B, its frame, again, is going to be defining its size and location in its superview, view A's coordinate system. So the frame origin is going to be 200, 100. It's 200 pixels in, 100 pixels down. And then its view size is going to be 200 by 250. So the entire frame of that view, the location and size in its superview coordinate system, is xy 200, 100, with height 200, 250. Now its bounds, since the bounds are in the coordinate system of the view itself, again, the origin is going to be 0, 0, and the size is going to be 200 by 250. It's the same as the superview. All right, so that's kind of the simple case. I'm going to talk about it a little bit more in depth. It doesn't get too much more complicated, but there's a little oddity here. And the thing that's a little strange about this is that frame is actually not a value that's ever stored on the view. Frame isn't, it's defined as a property on UI view, but UI view never actually stores the value of the frame. It stores a couple other values, actually a few other values, that it uses to compute the frame. So when you ask a view for its frame, it takes these other values and computes the new frame and returns it to you. If you set a frame, it actually doesn't store the frame that you set. It extracts the values it needs from it and stores those. So the first value that it stores is actually the bounds, which we just talked about. But we'll talk about that real quick here. So first of all, we've got that same view we were just looking at. We already decided its frame is 200, 100, 200, 250. That's the size and location in its Superviews coordinate system, just to repeat that. So that's not stored. The bounds is stored. The bounds is the size of the view in its own coordinate system. And in this case, again, we got 0, 0, 200, 250. So that's great. That tells us how big the view is, but it doesn't tell us anything about where in the superview the view is located. So the other property that's used for that is actually the view's center point. So in this case, we can see the center point is 300, 225. It's the point in the Superview's coordinate system that is at the exact middle of the view itself. And then the view's bounds is distributed evenly to the left, right, top, and bottom of that. So when we go to calculate the frame from the bounds in the center, we can take the frame point and distribute the bound size evenly to the left, right, top, and bottom, and that's how the frame is calculated. So when you go to set the frame on a view, it actually ends up figuring out what the center point would be and the bounds width and height, and saves those two values. So yeah, in this case, that's how we get back to 200, 100, 200, 250. 300 is the center point. That 200 is distributed evenly amongst each side. And then 225 is the vertical center point. And the 250 is distributed evenly above and below it. So that's pretty cool. But you might wonder why you would care about that. So this gets a little bit interesting when we start talking about another property of UI view. And that property is the transform. So the transform is actually really powerful and lets you do some very, very cool things. It's a CG affine transform, so it's an affine transform, which means it can define a scale, a rotation, and a translation. We'll take a simple example right now, and we'll just apply a transform to this view that's a 45-degree rotation. So what's that going to do? Well, pretty much what you might expect. Visually, it's going to rotate that view 45 degrees, and it's going to rotate about its center point, which is the other value that we've already got stored. So we still have the bounds, hasn't changed. Bounds is still 0, 0, 200, 250, defining the size of the view in its own coordinate system. Center point hasn't changed. Still 300, 225, defines the point in the superview that the bounds are distributed around. But now we've got a transform on this view as well, and the transform rotates at 45 degrees. So that rotation is happening before we're applying the bounds to distribute it. So the bounds actually get distributed at an angle. So what's that going to do to the frame? The frame's computed, and the frame is the rect of the view in its Superview's coordinate system. But now the rect of this view in its superviews coordinate system is no longer a rectangle. Now it's kind of a skewed diamond there. So the frame is not quite as simple anymore. This is where things get a little bit questionable as far as using the frame goes. The frame is actually now, come on, this. 140, 65, 320, 320. Yeah, you can check my math on that. I'm pretty sure I did that right. This is where the real definition of frame comes in. And one thing that you actually have to be careful of if you start using frame in conjunction with transform. Frame is the smallest rectangle that in the superviews coordinate system that fully encompasses the entirety of the view itself. So if there's no transform, no rotation, no scale, that's pretty simple. It's just the rectangle that's the bounds width and height with the center point used to calculate the rectangle of the view. When you've got a rotation, then it gets a little more complicated. It's actually the frame is defining parts of the superview that aren't actually covered by the subview. So that's just one thing to keep in mind when you start dealing with transforms. If you don't use transforms, you don't have to worry about it. The frame is pretty easy to deal with. If you're starting to transform your view, frame becomes a little bit less useful. You might want to start using center and bounds directly in that case. So yeah, when do you want to use frame and bounds? Do you have a question?
Yeah, is there a transparency feature in the frames? So can they collide? What happens if one frame is in the superview and another frame is in the superview, and the coordinates interact with each other?
So the question is there a transparency feature? What happens if two subviews overlap each other? And the answer is absolutely there's transparency. An entire view can have an alpha value applied to it to change its transparency, which will blend it with whatever's behind it. And also individual parts of the view's content can have alpha. So you can have sort of a fully opaque area in the center, like a circle. And the outer parts of that circle can be transparent and not occlude other views that intersect the view's rect. So yeah, absolutely, there's full support for transparency at a variety of different ways, actually. And we'll see some of those later on. All right, so we've got frame and bounds. Which one do we want to use, and why would we pick one over the other? Frame is often very easy to use when you're dealing in the superviews coordinate system. Again, as long as you don't have a strange rotation or a scale or something on there, it's pretty clear what it means, and it's very easy to position something based on the frame because it's four values, x, y, width, and height, that define the location and size of the view in the superviews coordinate system. So if you're using a view and you're going to position it in some superview, you probably just want to use the frame. It's almost 100% of the time going to work out just fine. It's only a problem if you start dealing with transforms. So if you're using a view, probably going to use the frame. If you're implementing a view, you're more often going to be dealing with the bounds. And this is interesting when we start talking about things like events and interactions. Basically, when you start talking about hit testing views and touches in the views, you're going to be talking about the touches in the coordinate space of the view itself. And the coordinate space of the view itself is the bounds. So in that case, you'll probably be dealing with the bounds. Yeah, it's kind of a matter of perspective. When you're looking at a view from outside, you're usually setting its frame. When you're working on implementing the view and looking at it from inside, you're usually dealing with the bounds. All right, so that's what a view is. That's how you position it. So how are we going to create them? So we talked about it a little bit already. In Interface Builder, you can just very easily drag your views out and place them anywhere you like inside of your window. So in this case, we've got the library view on the left there, and we've found just a plain basic view. We've dragged it out and put it in our window. Now, if you take a look at the polygon view identity here, we've actually defined that this particular view is a custom subclass of UI view. So there's quite a few predefined view types that UIKit provides for you, and those are all available from the palette there in Interface Builder. If you're defining your own custom subclass of UI view to do your own drawing or something of that nature, the way that you'll have to create that in Interface Builder is by dragging just a plain UI view out of the Interface Builder's library there, putting it in your window, and then in the inspector, you can change the class of that view. Interface Builder in its library won't show you your own custom subclasses. You'll drag out the plain view and then change the class style. And the reason for this is kind of that Interface Builder doesn't actually have the code to run your own view. The code is in your application. It's not part of Interface Builder. So it can't show you, for instance, the result of your drawing in the view. It'll just show you this empty frame. you can define what the class is. And then when it's created when you're running your application, all your code will run. It just won't show it to you in Interface Builder when you're designing it. So that's how you can do it in Interface Builder. What if we want to create them manually? If we want to do it in code, like we just talked about a little while ago, say you don't know how many views you need up front. You need n objects at runtime. How do you create them? So we need to do, in this case, we're going to be using the frame. We're going to be setting the frame, which is going to be positioning and sizing the view in its Superviews coordinate system. And we actually have a very convenient way to set that. When we create a new view, we'll do UI view, alloc, init with frame. So init with frame is UI view's default initializer. When you create a view, you're going to specify the view's frame. So for example, let's CG-rect make a rect that's 20 by 45, and that's XY, width and height 140 by 21. And we're going to create a label that's that size. So we'll call UI label alloc, init with frame, that frame that we just created. We want to add it directly to our window in this case. So we've got a pointer to our window. Presumably in this case, we're in our application delegate or somewhere else where we have a pointer to the window. So we'll call window add subview label. We'll tell the label to set its text. So label has a method called setText. And we'll just give it some text, number of sides. And this is just a static label. It's just defining the text number of sides. We're never going to change it again. We're not going to update it. We're never going to do anything with it again. So we don't need to save the pointer to it. And since we're not going to save the pointer to it, we definitely want to make sure we release it so that the superview has the only remaining retain count on it. So we'll call it label release. Label is now retained by the UI window. And when the window goes away, the label will go away. All right, so that's how we create standard UI views. What about defining custom views? If we've got our own drawing or our own different things that we want to do that aren't provided by the standard UI kit views, how do we do that? So for custom drawing, you'll subclass UI view and override the method drawRect. By default, actually, UI view doesn't implement drawRect. There is no implementation. Nothing draws in a normal basic UI view. So when you create a subclass of UI view, you can implement drawRect to draw anything you like in there. And we'll talk about how to do that in a little while. And if you're doing event handling, there's 4 methods that you override. These are actually defined on UI responder, which is that we just talked about earlier. It's the superclass of UI view. And that's touches began with event, touches moved, touches ended, and touches canceled with event. We'll talk a lot more about these in a later lecture about event handling. Just keep in mind that these are the 4 that you need to know about: began, moved, ended, and canceled. Those are the 4 states of a touch. If you implement any of them, you definitely want to implement all of them. We've been said some different things in the past, just want to make sure it's very clear. If you implement any of the touch event handling methods on your view, you want to implement all of them. All right, so you've got your UI view subclass. You've created it in Xcode. You've created a new UI view subclass. How are you going to draw into it? Well, we just talked about drawRect. So as I said, UI view's drawRect does nothing by default. If it's not overridden, then there's actually a property on UI view called background color, and you can set that to any UI color. And by default, the view's background will be filled just with that color. So its entire rect in its superview will just be filled with that color. If you want to do some custom drawing, you want to override drawRect, and that's where you can do all your custom drawing in there. So you've got this view. You've overridden drawRect. So when do you think it's safe to call drawRect? When would you? What do you think you'd do? When would you call it? Anyone? All right, well, you never, never, never want to call drawRect. The system calls drawRect for you. It's absolutely never safe to call drawRect. You really don't want to do that. The system knows when it needs to see the content of your view. It knows the best time to call drawRect. It's going to cache the results so that it doesn't get called every time that something needs to animate around on the screen. It's very efficient at when it calls drawRect, and it makes sure that it minimizes the amount of work that has to happen. So you really don't want to call it. You want to let the system handle that automatically for you. If you have some state in your application, so maybe your application's model in your model view controller design has changed, your controller can call setNeedsDisplay on the view to tell the view that it needs to redraw itself. So setNeedsDisplay is the thing that will tell the view it needs to be redrawn. The system will then take care of calling drawRect for you at the appropriate time. But if you just call it yourself, actually not only is it not efficient, nothing's actually going to happen in terms of things changing on the screen. It might crash, it might do other bad things, but nothing good is going to happen. The changes aren't even going to appear. You definitely want to just call setNeedsDisplay. So for example, you've got your controller. You have a method on it called setNumberOfSides, and that gets called with a new number of sides. So you're going to store off the new number of sides in your instance variable, and then you're going to just call polygon view set needs display. The system will take care of the next time the run loop turns, which is basically just the next, when you return from your event processing. The system will take care of calling drawRect for you. It'll update all the cached state that it has about the view's content, and the screen will get updated automatically. You just have to call set needs display. All right, so what do you want to do in your drawRect? Well, core graphics, I mentioned briefly earlier, it's the framework that defines those rectangles and points and sizes we were just talking about. It's also the framework that contains Quartz 2D. It's basically our 2D graphics library for doing basic drawing with vectored graphics. UIKit actually provides very limited support for any kind of graphics drawing operations in UIKit itself. It relies mostly on the functions that are provided by the core graphics framework. And core graphics is actually not an Objective-C framework. It's a straight-C framework. So you're calling a bunch of functions in there. You're dealing with not objects, just calling functions. It's, as I said, the Quartz 2D drawing engine. It's pretty simple, but incredibly powerful. It's, as I said, a vector graphics library, so it provides a bunch of things. The graphics context. The graphics context is the thing that you're going to do all your drawing in. It provides transformations. It uses the same CG affine transform struct that we talked about a little earlier on views, though it uses it internally to do transformations on the vector graphics drawing operations. It provides the concept of paths, which let you define basically regions of the screen that you can stroke and fill. It defines colors that let you specify the colors of what you're drawing. It has fonts and a bunch of other really cool stuff. So it does a lot of things. You can basically draw everything you want to draw using core graphics. So graphics context, that's the first thing I talked about there. This is actually what all of your core graphics calls will be drawing into. And the reason that you don't, well, and part of the reason you don't want to call drawRect directly is that UIKit handles taking care of setting up a graphics context for you before it calls your drawRect method. So when drawRect is called, there's already a graphics context created by UIKit that you're going to be drawing into. So all drawing is done into this opaque graphics context. That's opaque in the language sense, not in the graphics sense. You don't have visibility into the elements of the graphics context, but it may be transparent. It can be used to draw into the bitmap store, which is actually what backs every UI view. We'll talk about that in a little bit too. It can also be used to draw to PDFs, to memory context. So if you want to draw into a piece of memory for off-screen drawing, you can use context for that. You can draw into PDFs and save out a PDF. A context is basically an abstraction around all of these different backing stores. So it's really powerful, and with the same core graphics APIs, you can have multiple different destinations for your drawing. As I said, graphics context setup is automatically handled before calling drawRect by UIKit. It defines a few things, including a current path, a line width, the current transform. The transform by default is the identity transform, so there's no rotation, no scaling, no translation. If you're familiar with matrix multiplication, a CG affine transform, it's just a matrix, and the identity transform is just the unit matrix. You can access the graphics context within drawRect by calling UIGraphics get current context. This will give you back the CG context ref that UIKit created for you, so you can use that as the parameter in all your calls into core graphics to determine where you're going to draw into. And then you use CG calls to change the settings on that context, and we'll see some of those in a minute. But they let you do things like define the line width, the color that you're going to be drawing with, and then they also define all the graphics operations, like drawing circles and squares and lines and all that kind of thing. So that the context that you can get back with that UIGraphics get current context, if you call it within your drawRect, is only valid for the duration of the drawRect call. You absolutely do not want to copy that context off to the side and store it in IVAR or anything. It gets deallocated by UIKit as soon as drawRect returns, and it's no longer valid. If you save it, best case, nothing shows up on screen when you draw to it. Worst case, your application crashes. Don't save it. Nothing good can come of that. So there are a few wrappers around some CG constructs that are provided by UIKit, which makes some things that are a little bit more difficult in CG super simple. One of the great examples of that is UI color. It's not really hard in CG, but there's a few more calls that you have to know. And in UIKit, it's really easy, and it's an Objective-C call, so it sort of fits in with everything else you're doing. you can just call UI color red color, and that'll give you back a UI color that represents the color red. There's a bunch of these convenience methods. They're like red color, blue color, green, gray, black, white, all those things. You can also define a UI color with an RGB value or an HSV value. If you have one, so you've called UI color red color, and you want to set it as the current color on the current UI graphics context, that's the thing that we got back from UI graphics get current context, you can just call red color set, and that'll update the graphics context to use red as the color to do all drawing in for subsequent drawing operations. Yeah.
Does the interface builder use UI color in its color chooser?
So the question is, does Interface Builder use UI color in its color chooser? Not really. I mean, the colors that you're defining will end up at runtime as UI colors. So the color that you pick, it's kind of, it will end up creating a UI color at runtime, but in Interface Builder itself, it's not really using UI color. Yeah.
Can you do it as a one-liner, or does the color need to be allocated somehow?
So the question is, can you do it as a one-liner, or does the color need to be allocated? So what do you think the retain semantics of this are, just based on what we learned about retain release and allocation?
It would need to be retained so you can see what it is, so it's compared to for reference.
This is a convenience method, right? It doesn't have alloc, it doesn't have copy, it doesn't have create in the name of the method. So when you get it back, its retain count is 1, and it's auto-released. So it's in the auto-release pool. So if you do nothing with it, it's just going to get auto-released at the end of the run loop when the pool is drained. So yeah, you could actually do this on a single line. You could just call UI color red color set. You might want to store it in an instance variable if you were going to swap between multiple colors in one piece of drawing code. So at the top of your drawing code, you might just want to call UI color red color, have it in a local variable, UI color blue color, have it in a local variable. Then as you go through and draw, you can just call red color set, do some drawing, blue color set, do some drawing. And you don't have to keep calling the UI color method, but honestly, that's kind of a over-optimization. It's not expensive to call UI color red color, so yeah.
So you said subsequent drawing options, so if you want to change the color of something that's already been drawn, is it you do this and then you would do that needs to be redrawn thing?
So the question is, I said that it changes the color for subsequent drawing operations. What if you want to change the color of something that's already drawn? If something's already drawn, you'd have to redraw it in order to change its color. So if you've already drawn something in the view and you want to go back and make it blue now, you do have to call set needs display, and then the next time through you can use red as the color when you draw it. But before you do any drawing, you have to set the color that you want to draw it with. Any color that you set afterwards will change the color of things that you draw after that, but not stuff you've already drawn. So it lets you in one pass use multiple colors to draw different parts of your content. But yeah, if you need to change something, you have to redraw it all. And then the other thing that UIKit provides on top of core graphics is the UI font class, which gives you access to a system font. There's a convenience method for that, system font. And actually, you can specify a system font of a particular size, and it just takes a point size. You can also get a font by name. There's actually a few fonts available on the system by default. UI font has another convenience method that lets you get back, the name of all the fonts that are available. So if you just call that, I actually don't remember the name of it off the top of my head. I think it's called all font names or all fonts or something. It'll give you back just the array of all the fonts that are available. You can look through them and figure out what they are and then try them out yourself. You can also actually specify your own font. You can bring a font with you as a resource in your bundle. It's a little bit more complicated, but you can still load it by name as a resource and then use your own font if you have one to ship with your application. All right, so let's take a look at a simple example of drawRect. Take a look at what we can do here. We're going to draw just a solid color, a solid shape with a color. So we've got our drawRect. We've got our self bounds. We're always drawing in our own coordinate system, so we're going to get our bounds. We're going to call UI color gray color set because we want to draw something with gray. And then we'll call UIRect fill bounds. So that's going to, UIRect fill is one of the few convenience methods provided by UIKit. It basically fills the entire rectangle that we pass in with the current color that was just set. So that gives us, it fills the entire bounds of our view with gray. So then we can get another rect we'll call CGRect make and create it with XY of 1010 and width height of 50, 100. We'll set a red color and then call UIRect fill again on this square. So that's going to fill in just a little rectangle that's a small part of our view. And finally, we'll call black color set and then call UIRect frame, which is just going to outline that rect that we just defined there. So what do we end up with? Well, it's pretty much what you expect. We've got a full gray background on our view, a rectangle that's filled with red, and it's framed in black. All right, so there's actually more complex drawing operations you can do with core graphics as well, beyond just rectangles, although for that you actually do have to drop down to using core graphics C functions directly. UIKit doesn't provide any kind of wrappers around them. So in order to do that, you'll get the current graphics context with the function we saw earlier, UI graphics get current context. You'll define a path, which we'll talk about in just a second. It's basically a bunch of lines that are grouped together that define the shape that you're going to be drawing. You'll set a color, and then you can either stroke or fill that path. Stroking it would draw the outline, filling it would fill it in. And then you can repeat that as necessary to draw all kinds of different shapes. So this is kind of the cop-out route. These are just keynote shapes here, but you could actually draw these using core graphics yourself. You would define them as paths, and you could, for instance, the rounded rect over there, you'd draw a line with a little rounded corner, a line, rounded corner, line, rounded corner. Basically, you can define arbitrarily complex shapes using these core graphics-based functions, and then stroke them and draw them and fill them and do all these great things. So yeah, they're made up of lines and arcs and curves and rectangles. And the operations that you'll be doing to get that are creating and drawing paths. And those are actually two distinct things. So as you're creating the path, you're defining the shape. You're drawing the circles, you're drawing the lines. But while you're doing that to create the path, nothing is actually showing up on screen or being drawn. You're just defining the shape. Once you've closed the path and you've finished defining all that, that's when you actually draw it. And that's a separate operation. So first you define the path, then you draw it. The object, for lack of a better term, that you'll be using to define the path is a CG path. There's actually two parallel sets of functions that you can use for paths. There's some convenience ones on CG context. So CG context is the graphics context we were looking at that you get back from UI graphics get current context. There's actually an implicit default path on every CG context. So if you just need to do a quick shape and you're just drawing a simple thing in a context, and you don't need to reuse it, and you don't need to draw it multiple times or do anything more complicated with it, you can use the implicit path that's defined on the context. And there's functions specifically for accessing this implicit path. So you can tell the CG context to move to a point, to add a line to a point, add an arc to a point. There's a whole bunch of other ones as well. And then you close the path when you're done, and then you either fill it or stroke it. If you need to use the path more than once, or if you want to save it so that you can draw the same path again later and you don't want to have to recreate it every time, that's when you might want to start using the CG path object itself. And it has all the equivalent functions that are available for CG context, but it's creating the path as a separate object that you can actually store as an instance variable and reuse multiple times. So yeah, there's kind of two ways to create paths there. So let's take a quick look at a simple example. We've still got our drawRect here. The first thing we have to do is get the current context. So we call UI graphics get current context. That gives us back the CG context ref that UIKit created for us. It's already got some default values set, but we're going to set the color to gray and then fill a rect again. So our background is again just a gray rectangle. Now we're going to call CG context begin path. So this tells the context that we want to start creating this implicit path on the context itself. Then we'll move to point, so we'll move over to 7510. We'll add a line to point 10150, add a line to point 160 150, and then close the path, which actually connects the last point that we went to the first point. Then we're going to set the red color and set that as the fill color. We're going to set the black color as the stroke color, and then we're going to call this other function here, CG context draw path, with the option path fill stroke, which tells it to both fill and stroke the path. So in one operation, we're going to fill it and draw its outline. Anyone have any idea what we're going to see show up when we call this? What's it going to look like? Oh, come on. No? What are those? There's only like 3 points there. How many objects can we have that have 3 points? All right. So we're going to get a triangle. It's filled with red, and it's surrounded by black, as we just expected. So, and it's got the gray background, which we got from calling UIRect fill at the beginning there. I don't know. You guys need some geometry, I think.
Can you go back to the last slide really quick?
Yeah, sure.
What's the K in that last function? Is that a typo, or what does it stand
The question is, what is the K in the last function? It's kind of a legacy naming convention, I guess. So KCG path fill stroke it's a value in an enumerated type. And historically, we don't really do this in UIKit, and a lot of other frameworks don't do it either. But all of CG and a bunch of other frameworks have the standard naming convention that constant values defined in an enumerated type start with the letter K, just to indicate that they're a constant value from an enumerated type. So KCG path fill stroke it's a value from an enumerated type. It's not a typo. So a little bit more information about drawing. You can find some stuff in the UIView class reference. There's a little bit there that talks about a bit about drawRect and that kind of stuff. A ton of it in the CG context reference and basically the Quartz 2D graphics reference. Quartz 2D is core graphics. They're just two different names for the same thing. And there's a ton of samples on the iPhone Dev Center that cover all sorts of different drawing. So that's basic shapes. But we also might want to draw some images and text at different points. So Core Graphics provides the ability to do this as well. So let's take a look at how that'll work. UIKit actually provides a convenience function wrapping the Core Graphics image functions. And that convenience function is UIImage. So UIImage is a class in UIKit that represents an image. And the image can come from a few different places. We can fetch it out of the application bundle using UIImage image named. So if you, in your application bundle in Xcode, in Xcode when creating your application, if you drag an image in there, like a PNG image, when you build your application, it'll actually be copied into the application bundle, which is the grouping of resources used by your application. And then at runtime, you can get that back by calling UIImage image named and then the name of the image. One thing to keep in mind there, the image name actually includes the file extension. So if you've got, for example, myimage.jpg, and you call image named myimage, you'll get back nil. Nothing's going to load. If you call image named myimage.jpg, that's how you load that image out of your bundle. You can also read an image from a file on disk that's not in your bundle using UIImage init with contents of file. Obviously, you actually call UIImage alloc init with contents of file. And then you pass the path to the image on the disk. And finally, you can actually create one from in memory. So if you've downloaded something off the internet or you just happen to have the bits in memory to represent an image, you can call UIImage init with data nsdata, and that'll give you back a UIImage representing that in-memory image, decoded and ready to use. So even if you had a JPEG in memory, it'll decode it for you. You can create images from a particular CG context. This is actually pretty cool. If you need to create basically an image programmatically that you want to reuse later for multiple different things, this is one of the cases where you'll be creating, well, there's some convenience functions in UIKit to create it for you, but you're actually defining a new CG context, and the backing of that CG context will be a piece of memory that will be used as a UI image later. All the operations that you'll do on it are exactly the same as the operations that you'd be doing when drawing into a view. You'll basically just define the size of the image that you need, and then you can call these core graphics operations that we talked about before to draw your own image programmatically at runtime. Basically, the way you do it is you create this special graphics context, you define the size of the image that you need, draw, and then capture the context as a bitmap. Let's take a quick look at that. So let's say you want to define a function called polygon image of size. And you'll pass in the size that you want of this image, and that's going to define how big the UI image is in width and height in pixels. We'll call UI graphics begin image context. So this is a function in UIKit that tells UIKit to create a new CG context ref that points to a piece of memory that is as big as size. You can call all your normal drawing code there, any of the normal CG context things that you'd have called before. You can call UI graphics get current context to get the context it created for you. When you're done, you call UI graphics get image from current context. And this returns you back a UI image that represents whatever it was that you just drew using core graphics. And finally, you call UI graphics end image context to clean up after yourself. And then you can return result, and you've got a new UI image there that you can do anything that you'd have been doing with any other UI image loaded from disk or otherwise gotten out of memory. Once you've got all that stuff, you've got a UI image object. You might want to store it out to disk or send it up to a file server or something. You can get back basically an encoded representation of it as either a PNG or a JPEG using these two functions, UIImage PNG representation and UIImage JPEG representation, returned you back an NSData object, which is basically just raw bytes that are encoded, the encoded data of the image, either as a PNG or a JPEG. UI image also has this property that'll give you back the CG image ref. So CG image ref is the thing that we're wrapping here. The CG image is the core graphics image. It's the object defined by core graphics to represent an image. UI image is just a wrapper around that. And in fact, there's a property that lets you get at the CG image. You might want to do that. We'll see why in a little bit. If you actually want to use some of the core graphics image manipulation functions, you can. UIKit actually provides a bunch of drawing functions for images, drawing methods on UI image. But there's also some defined on CG context. CG context draw image. Actually, I don't remember the exact function name, but something like that. So if you want to use those, you can call image CG image, and it'll get you back the CG image ref that you can call use with core image. With core graphics. So yeah, how do we draw these images? We've got our UI image. We loaded it off disk, or we created it programmatically with UI image begin image context. So now we've got it. We can call draw at point on that image, which will draw it at the exact size that the image is defined to be, but with its origin at that point. So if we draw at point 0, 0, it's going to draw it top left, and then it'll extend as far right and down as the image data requires. You can call draw in rect, which will let you specify a rectangle in which to draw, and that'll actually stretch the image to fit within it. So if you had a 10 by 10 image, and you called draw in rect with a rect that was like 20 by 10, it'll actually stretch it horizontally to fit that. As long as you keep the aspect ratio the same, then it won't change. It won't look squished or anything. But you actually can squish them that way. And finally, we've got draw as pattern in rect, which also takes a rectangle. But in this case, instead of stretching the image to fill that rect, it'll draw it as many times as necessary to fill the entire rectangle. So basically, it tiles it to fill the entire rectangle that you specify. And finally, we talked about strings. When we talked about foundation, we have NS strings. So we can still use those NS strings. We can create them the same way we were creating them before. But maybe we want to draw them now. And we can do that in our drawRect with NS string method draw at point with font. So we saw UI font a little while ago. You can get the font. And then you use that with this method in order to specify where in your graphics context this string should be drawn and with what font. But there's a better way. So specifically, a better way to do drawing and getting images and text on screen. You can do it in drawRect, and that's interesting in some cases. But more often than not, you'll want to use some of these other things. And there's actually some UIKit views that make this really easy to do and enable a lot of other really cool features. When we start talking about animation, we'll see kind of what that'll be and why you'd want to do it this way. But just quickly, let's talk about what that would be. So how do we want to implement this? So the first thing you might think of here is maybe you want to specify a rectangle, or sorry, a view at the bottom that includes the entire area of that octagon. Use some CG calls in order to stroke the path of the octagon there to make it purple. And then use NS strings draw at point with font to draw that text. And you can absolutely do that. That'll definitely work. But it's not so great if you then later want to animate things. So if we actually wanted to move that text relative to the surrounding object, that's actually, you can't really do that if you're doing drawRect. These are embedded devices. They're pretty small. They're powerful, but they're not powerful enough to do animated calls to drawRect. You can't drawRect every frame. So if you need to move something relative to something else, you actually want to have them in separate views. And we actually have some very convenient views that let you deal with images and text, so you don't have to write your own every time you want to do that. So yeah, as I said, we've got this polygon view that displays the shape and the name. We probably don't want to just draw the text right in there. That would be inefficient when we're animating. So instead, we'll use UI label, which knows how to draw text all by itself. It has a whole bunch of properties on it that do some really cool things, including letting you set the font, the text color, the shadow offset, and the shadow color. If you look at a lot of the text on the iPhone, much of it is either embossed or it looks like it has a little shadow. For the most part, that's always UI label doing that drawing. And you can just use UI label and get that behavior yourself. You can draw like a little black or white shadow behind your text. UI label knows how to do that. You don't have to write the code yourself. And finally, you can specify the text alignment. So this is actually really convenient because otherwise you'd have to measure the text and figure out how to lay it out yourself if you wanted to center a piece of text. Don't bother. UI label knows how to do it. You can set the text alignment on the UI label. It's a subclass of UI view, and you can put it in your view hierarchy. It'll handle centering it or doing whatever you need based on the text alignment property. Second, we've got UI image view. So UI label is great for text. UI image view is great for images. The properties on that, there's a few of them. They include image. If you're just setting an image, it'll take the image that you've got, your UI image, and it'll display it in its frame. You can get a little more complicated than that, though, and do an array of animated images. If you know about like animated GIFs from the good old days of the internet, this basically lets you do that. So you can have all your users incredibly annoyed at the flashing blip on your screen. You can set the animated duration and the repeat count. So the repeat count makes sure that that animated GIF keeps repeating forever so your users can't stop it. There's another property on UI image view called content mode. Actually, this is on UI view, but it's most useful on UI image view. And it lets you specify how the image that you're setting on your UI image view is mapped to the bounds. So if you've got a UI image view that's 100 by 100 and your UI image that you're setting on it is only 50 by 50, content mode determines where that image is going to get drawn in the bounds. So you can specify top left, top right. You can specify stretch. You can specify aspect stretch. So if you have an image that is taller than it is wide, it'll make sure it's centered horizontally, but then fits in vertically exactly. You can specify aspect fill. So in that same case, it'll make that image as big as it needs to be to fill the horizontal area and then clip the top and bottom. All right, so we have UI label, which does the text. We've got UI image view, which does the images. The other thing that is pretty useful, it's a subclass of UI view, is UI control. We talked about that a little bit too. It has some similar properties to UI label that let you draw, basically define how the text in the control is going to look. It has a selected and an enabled and a highlighted. So that's UI button has those things. UI control is the superclass. It doesn't draw text itself. The subclasses of UI control know how to draw things. And UI button knows how to draw a lot of the same stuff that UI label knows how to draw. The font, the title, the image color, a background image, a bunch of stuff like that. Anyway, you can see the UIKit headers. There's plenty of information in there about how that works. So now let's talk about some of the really cool things that you can do with animation. So we've got these views, and they've got all kinds of content, and we've got them up on screen. And now you want to move them around because the user interface on the iPhone is very fluid. A lot of stuff is animating around. Things are moving. It's pretty cool. So we want to do that with our own views. So we've got our controls up top. We've got our drawing at the bottom. We're going to flip that switch. And when we do, we're going to animate the thing down, and those controls are going to fade in. This is actually incredibly easy to do using UIKit. And there's actually a framework that we sit on top of called Core Animation that implements a lot of this animation stuff for us. It's really powerful, and this is the stuff that I'm just most excited about. It's really cool what you can do with this. So UI View actually supports quite a few animatable properties. Core Animation supports even more. If you want to drop down to Core Animation, you can do even more down there. Every view, well, we'll talk about this in a bit, but every view has a layer, which is the core animation object, which you can operate on and do all the extra core animation work. So for UIKit, we can animate the frame, we can animate the bounds, we can animate the center, we can animate alpha, which will change the opacity, and we can animate the transform to scale and rotate things. When you're setting up these animations, you basically set them up as blocks. So you define a start point and an end point, and everything that you set within that block is automatically animated by UIKit. The animations, they run asynchronously and automatically for you. You don't have to set up timers. You don't have to worry about dealing with all the callbacks or doing any kind of crazy redraws yourself. You basically just set up this animation block, change your properties, and everything just happens. There are some other options that you can specify on these blocks. That includes a delay before starting. So if you set up your animation block now but don't want it to start for half a second, you can set the start time delay, and those animations won't begin until half a second later. You can start at a specific time, so you can just wait a defined amount of time. You can define the curve, which is basically the timing function. So it determines how fast the animation progresses. So if you're animating from point A to point C over the course of 2 seconds, the default curve is ease in, ease out. So at the beginning of those 2 seconds, the progression is going to be pretty slow. It'll be pretty fast in the middle, and then slower again at the end. There's other curves you can define, including ease out, ease in, and linear. So linear, the progress is linear over the course of that time. The speeds remain constant. Ease in, it starts slow and then gets faster. Ease out, starts fast and then gets slower. So that's the animation curve. And a repeat count to determine how many times that animation is going to replay. without you having to do anything else. You won't have to restart it or set it up again. You can have it repeat multiple times on its own. And also auto reverses. You can basically have the animation, once it gets to the end, turn around and play the exact same thing backwards, back to where it started, again, without any more interaction on your own part. And the combination of those two things, repeat count and auto reverses, can let you set up an animation that keeps happening multiple times, all at one time. You don't have to even go back and change the properties. You don't have to keyframe it or do any crazy things. You can set it up at one time at the beginning and just let it go. So let's take a quick look at an example of that. We're going to call the Show Advanced Options button. When the user flicks that switch on the little sample we just saw, we're going to call this code. And the first thing we'll do is call UIView begin animations context. So when you begin an animation block, you can name that block. There's some delegate methods later that you'll see where you can reference this name. For this case, we'll just call it advanced animations. You can pass a context pointer, which is basically any object you want. When the delegate methods get called, they'll get this context pointer. So if you have some particular data that's associated with this set of animations, you can pass it in there. And you'll get a callback when the animation finishes. And in that callback, you'll get past this context pointer. So you can sort of match your creations with the callback later. In this case, we're going to set the duration to 0.3 seconds. Durations are always floating point values, and they're always defined in seconds. So 0.3 is 3/10 of a second. We're going to set the options views alpha to 1.0. So we're going to assume that at the beginning, when our program started running, the options view, that view with those extra buttons, was totally hidden. It was opaque. It was totally transparent. And so its alpha was 0.0. We're going to set it to 1.0, and that's going to happen over the course of that 0.3 second duration that we defined. And it'll happen with the ease in, ease out animation curve, since that's the default. We're going to move the polygon view down. So we'll get its frame, adjust the origin, the Y origin of the frame by 200 pixels to move it down, and then we'll just set it back. So polygon.view.frame equals that new polygon frame we just defined. And that's going to automatically implicitly animate that view. And finally, UIView commit animations will end this block. So as soon as we're done with all setting that up, we return from the processing of our event. Those animations will begin automatically. We don't have to do anything else. And in fact, since we don't necessarily care when they finish, that's really all we have to do to set up all the animations we saw before. If we did care about when the animation finished, you can set up some delegate methods. There's another property you can set with the view animation block. That's the set animation delegate, which lets you specify some object to receive these delegate messages when the animation begins and finishes. And the delegate methods we can set are animation will start context, which is, again, that context that we passed in, and the name that we passed in when we called begin animations. Animation did stop, finished context. The finished thing is a little odd. It basically, when this is called at the end of your animation, it'll tell you whether the animation ran to completion. So there are things like starting another animation of the same property on the same object that can interrupt the previous animation. If it's interrupted for a reason like that, it'll tell you that in the finished argument by saying that it wasn't finished. Otherwise, as long as it ran all the way through and got to the final point, finished will be yes. You can also provide custom selectors for this using the set animation will start selector and set animation did stop selector, also properties that you can set inside of that view animation block. One thing to keep in mind during all of this is that your view hierarchy is only ever in one of two states during this. So you've got your view, and you're animating from, say, frame 0 to 200. At the beginning, before you've done anything, the frame's Y offset is 0. You set up this animation block and call setFrame200. If you then turn around and ask for the frame, it's immediately going to say it's 200, even though on screen it still hasn't moved anywhere yet. The view themselves are only in one of the two states. There's never an intermediate state. It'll never say view frame returns 150 during the middle of that animation. It's either 0 or 200. 0 before you start, 200 after you've set the property. There's actually 3 copies, basically, of this view hierarchy. We won't get into this too much, but there's the layer tree, which is basically your view hierarchy. That's what you're working with. And that's the thing that's always in one of two states. There's a presentation tree, which we won't really see much, but if you cared about where through that animation you were, you could get the presentation layer and query its frame, and that would tell you halfway through the animation that it was halfway through. And finally, there's in a whole separate process a render tree, which is basically what's being drawn on screen. The only thing that, for your purposes, for dealing with applications, for the most part, you're ever going to have to care about is the layer tree. Yeah?
So is it possible to synchronize different animations?
So the question is it possible to synchronize different animations? And the answer is absolutely. These things are actually transactional. I don't know why I couldn't think of that one. Within one turn of the run loop, so basically you get an event that says the user tapped. Everything that you do before you return back to the run loop to finish that tap processing is committed to the rendering as one transaction. The entire thing is a single transaction. So any animations that you set up within that single callback about the user having tapped, they're all synchronized automatically by virtue of the fact that they're transactional. So none of them start until you're done setting all of them up and return back to the run loop. So it makes it really easy if you're setting up multiple things in one pass, but multiple animation blocks, they're all implicitly synchronized. So how does all this work? Do we call drawRect every frame and draw the different progression as we're going through that? Well, I already kind of alluded to that as I was mentioning. These devices aren't powerful enough to call drawRect that much. Is it magic? And it kind of is, but it's magic that's understandable once you know a little bit about it. So all of this is built on top of another framework called core animation, which is what drives all of these animations. And it's basically an accelerated rendering engine. On the new iPhones, it's actually all done using OpenGL at the low levels, although for the purposes of using it, you don't actually have to know anything about OpenGL. It animates all of these different layers in an accelerated fashion using the OpenGL graphics renderer. So every UI view is backed by a separate CA layer, and a CA layer is the object that core animation creates to represent a layer. You can actually get the CA layer from the view, as I mentioned. And the interesting thing about this is that every view, so every CA layer, has its own backing store. So in traditional systems, back sort of in the old days, the old Mac OS days and early Windows, basically applications were drawing directly into the frame buffer. You had a big piece of memory that represented what was on screen. Applications drew directly into it by writing bits into that memory, and that showed up on screen. Then with Mac OS 10 and some of the newer versions of Windows, there was this new compositing model that was introduced, which was really cool. Basically, every separate window had its own backing store. Applications drew not to the screen frame buffer, but into the window backing store. And then there was a compositing pass, another process that would run and take all of those backing stores, composite them together, and make the final screen image. Core animation takes that one step further. Now, not only does every single window have its own backing store, but every single view has its own backing store. So every view that you have has a separate piece of memory that represents what's drawn in that view. And this is what really makes a lot of these animations just super fluid and incredibly easy to do. Basically, if you have two views that overlap each other, drawRect will get called once for each of those views to draw the entire content. And even if you fade one out or move them relative to each other or change which parts occlude other parts, drawRect never has to get called again because each of those had its own backing store. So at all times, core animation has a full copy of what each of those views would look like if it wasn't being covered up by the other. So they can be moved relative to each other. It never has to call drawRect again. It knows what they look like. It can just recomposite them. So the drawRect results are cached. That's what that means. Every view caches its results of its drawRect in a separate backing store. And those cache results are what are used to render the actual view. That's actually done by a separate process. I mentioned that there's the layer tree, the presentation tree, and then the render tree. The render tree is the thing that is actually the cached results of all these. It's in another process. It's not even in your application. So even if your application is hung, if you're doing, please don't do really, really long processing on your main event loop and block processing of touches and stuff. But if you did, animations you had already set up would just keep running because they're actually happening in another process. Yeah, as we said, those property animations are done automatically by manipulating layers. You set those properties on the view, the layers implicitly get animations set on them. I think we're kind of running out of time here, so let's kind of go through this real quick. Every view has a transform property. We talked about that already a bit when we talked about frame. The transform lets you rotate it, scale it, translate it, defaults to the identity transform. The CG affine transform structure is the structure defined by core graphics that defines these transforms. There's a few convenience methods. You can scale a transform, you can rotate one, you can translate one, you can create one. These are just a few of them. You can look them up yourself in the headers and the documentation. There's more information about all of this in the iPhone OS programming guide, modifying views at runtime, and the core animation programming guide. Real quick, the assignment 3 is going to be posted if it's not already. just a quick hint about some stuff that you'll have to know for that. Saving state across app launches. There's the NSUser defaults object, which is defined by Foundation. It's used to read and write preferences and state. You can get a single, it's a shared, it's a singleton object. You call NSUser defaults standard user defaults, gets you the standard user defaults object. Then from that, you can call integer for key or set integer on it, which lets you set and store integer values. And you can call object for key and set object for key, which lets you save and restore any coding compliant objects. There's the NS coding protocol. It's not real important right now what that is. Basically, dictionaries, arrays, NS numbers, any of the base foundation types we already talked about can be saved and restored using object for key and set object for key. So it's a great place to save and restore small amounts of application state. You wouldn't want to use it as a database for your music collection or massive amounts of things, but it's a really good place to store small amounts of state across application runs. So any questions? Yeah?
Is there any SQLite?
Question is there an SQL or SQLite? And there is. Actually, the SQL library is included on the iPhone, and it's available as API to use directly. There's also another class that wraps it. There's actually a whole framework that wraps it called Core Data. Core Data it's basically, it's really designed to be an optimal wrapper around SQL, or around SQLite, actually. And there's some other classes that interact with it to make displaying information that's stored in an SQL database inside of some UIKit views really easy. And we actually are going to talk about that later on in the semester, so we'll see how all that works.
So the best practice is to use SQLite or store it in a file?
Question is, best practice is to use SQLite or store it in a file, and it kind of depends on what you're trying to do, really. I mean, if you've got a small amount of data and reading the entirety of it up front isn't that expensive because it's not very much, storing it in a flat text file or a plist, it's not that big of a deal because it's not very much. If you've got a lot of data and you're going to be changing it at different times, or you just want to load bits of it at a time, absolutely use either SQLite directly or probably more likely Core Data, because it can be really efficient about memory management and it only reads parts that are necessary. But if you just have a small amount, just a flat text file or SQL or plist is great.
For more, please visit us at stanford.edu.